Hello, everybody. Good evening and welcome to this live stream program brought to you by the North Carolina Museum of Natural Sciences. My name is Chris Smith. I'm curator for the Daily Planet Theater here at the museum, which is actually pretty close to me right now. I'm actually bringing the show to you tonight. Okay, the show is actually coming from our digital media technician, his studio space, but I happen to be with you from the third floor of the Nature Research Center, which houses our Beyond Our Planet gallery. So this seemed like a pretty cool place to host a program all about astrophysics. Tonight, we're partnering with North Carolina State University's Department of Physics to have a discussion and presentation all about the winning science of this year's Nobel Prize in Physics, all about black holes. That's right. I know you love to love them. Black holes fascinate everybody in the universe, at least everybody that I know, because they are so mysterious and so fun to learn about. Black holes just do really cool and interesting things, but I don't know very much about them. So we've got somebody who does. From the Department of Physics, Sam Flynn is a graduate student in theoretical particle and nuclear astrophysics. Sam, welcome to the program.
Hi, Chris. It's nice to be here in orbit around the Earth and talking about black holes tonight.
I know you've got a great vantage point to talk about black holes. There might be one somewhere in your field of vision there.
Oh, I hope not. That's very dangerous.
Right. I've heard that these things can be a little bit dangerous when you get too close.
Absolutely.
Well, everybody, I hope that you've got a relaxed spot there on the couch. Get ready to learn something new all about black holes and explore the science behind this year's Nobel Prize with Sam Flynn. Sam, show's all yours.
All right. Well, as Chris said, thank you for joining us. I know there's lots of ways you could spend your Wednesday night, and you chose to go to a physics lecture, which makes you a very special kind of person. So I'm going to be talking about the 2020 Nobel Prize in Physics, which is an instance where nature divides by zero. As Chris mentioned, it's all about black holes. And so tonight, I'm going to try and give you an impression about all of the work that went into this Nobel Prize. And let's go. Okay, so let's begin not by talking about a black hole, but about nature's elegance in designing engines. This is a star, as everyone can see. And a star is a very elegant engine designed by nature. I'm going to artistically render this star for the rest of the discussion as this symmetric orb of hydrogen gas. When a baby star is born, gravity just pulls together a bunch of this hydrogen gas, the lightest element that we know of, and it makes this sphere. Gravity then continues to pull on it, inwards in all directions. So this thing contracts and contracts and contracts. And just like a pressure cooker, the inside starts to get really, really warm. In fact, it eventually gets so warm that it undergoes nuclear fusion, something that we haven't quite nailed here on Earth. In this process, it's essentially burning hydrogen fuel to make a new element, helium. So as gravity contracts then, the engine in the center starts to heat up, it makes helium, and it gives off energy in the form of light, which radiates outwards from the star's center. This pushes against gravity, and everything sort of evens out. Eventually, though, we're going to burn all our hydrogen fuel, leaving behind a core of helium ash. Without this light pushing outwards again, we're going to start to collapse. And this happens until we run out of hydrogen, in which case we have to do this cycle all over again. So these massive stars do this cycle where gravity compresses them, heats them up in the center. They burn old elements into new ones. They make light, which pushes out against gravity, and thus the star burns again. And it does this over and over again until there's nothing left but a core of iron ash. At the center, once it's made all this iron ash, the star is close to death. Iron cannot be burned by this process. It's actually ash. Just like with fire, once you burn up your wood, there's nothing else to burn. But gravity is still there, and it starts compressing the star further and further. It gets hotter and hotter and hotter, but there's nothing left to burn until it explodes in this brilliant display that we call a core collapse supernova. It ejects a lot of this gas out into the atmosphere of space, and ejects a lot of light that we can see millions of light years away. But there's still some leftover stuff which we call a remnant. Well, gravity doesn't go away even if that remnant can't be burned. If that remnant is massive enough, gravity just pulls and pulls and pulls seemingly without end until we have not just the death of some massive stars, but the birth of some black holes. This is an artist's rendering of a black hole, the thing we all came to see tonight. And you can see the black hole in the center and some of this ejecta, some of this leftover matter circling around it. So black holes are actually kind of well known. In fact, most of the quirky features of black holes that I would talk about are things that you sort of know. A black hole is by definition something that is so dense that at the center, gravity prevents light from escaping. And that's why the center of a black hole is black. Nearby light is so affected by this gravity that instead of moving in apparent straight lines, it's actually bent around it, giving you these distortions that you can see on this picture. This is light nearby being bent by the gravitational pull of this incredibly dense object. Other things start to happen. If you've seen the movie Interstellar, you might know that time starts to act funny as you approach a black hole. It gets slower as you get closer until it almost seems to stop at the edge of the event horizon. Speaking of which, black holes are defined by a certain perimeter around them, which we call the event horizon. This is a boundary where if you pass it, nothing escapes. There's no way to go back. No light, no matter, not even information can escape. This is much cooler than the vacuum cleaner that black holes are sometimes depicted as in media. It's literally a do not pass boundary. Matter nearby can continue to fall in, like making these accretion disks that we'd see here, which makes it hotter, kind of like our star engine. And that emits all sorts of radiation. And the most important black hole fact is that they're objectively awesome. Our timeline from when black holes were first postulated to now spans about 100 years. It all starts when Albert Einstein published his Theory of General Relativity in 1915, and it's impossible really to talk about black holes and the work done here without mentioning Einstein. He did win a Nobel Prize for that. It was actually his second. A year later, actually it was a month from December to January, Carl Schwarzschild provides the first solution to Einstein's new theory. And that very first solution implies this weird object, the black hole. We didn't really know what to do with this. This seemed like a very strange object. And it was not until around the 1960s that Roger Penrose, one of the Nobel laureates, proved that black holes are not an error in how we're solving the equations or setting up the problem, but in fact, a consequence of general relativity, something that it predicts. Years later, we turned our telescopes towards the center of our galaxy, found a very bright radio source there, and two teams, one led by Reinhard Genzel and another by Andrea Ghez, measured this object, concluding it to be a massive, in fact, supermassive black hole at the center of our galaxy, weighing about 4 million times the mass of our own sun. This is all really cool, and hopefully these are things you might have heard if you're coming to this lecture. What I would like to focus about through this talk is how do we know all of this? The things that I just mentioned, time acting funny, light being trapped, this event horizon, seem crazy, especially when you consider that they were predicted nearly more than 100 years ago. How do we, scientists, decide that this is a real object when we can't travel to one and see it? In fact, you can't even really point a telescope at it, you don't see any light from it. How do we know that we're confident in our answer? And how do we know that this isn't just science fiction? This is a really important question. And a lot of the work that went into this is slowly answering this question. So my talk is going to be structured in 4 parts. I know that my abstract said it would be in 2 parts, but that's what happens when you write the abstract a few weeks before the talk. In the first part, I'm going to talk about how the scientific method works and what the process of modern science actually entails. How do we come to answers to our questions so that we can be confident? Next, it is impossible really to talk about this work without discussing general relativity. And so I'm going to give you a very, very, very brief overview of the kind of things general relativity deals with. In the third section, I'm going to talk about efforts to solve general relativity and how it predicts black holes, why they made us so uncomfortable, and why they get to do all these crazy things, and how Roger Penrose showed us that this is in fact something we should really predict. And finally, I'm going to talk about some of the efforts in detecting black holes with observation, another important part of the scientific method, and in particular, how we measured Sagittarius A star, the supermassive black hole in our own backyard. As I go through my talk, these icons for each of the 4 parts will be appearing in the top left-hand corner of the screen. If you wonder why I'm talking about this, it is to get towards this topic. So without further ado, how do you philosophize about nature? Sir Isaac Newton, hopefully you've heard of him, is basically the modern father of physics. We consider him the father of all physics, and he was one of the first natural philosophers, which we now call physics. When he wrote his big magnum opus, the Principia Mathematica, he laid out some things that he wanted to aim for in this new theory of science. And these things are still important to us today. These 4 guiding principles are A, we need to admit no more causes than are both true and necessary to explain the effect. Meaning, the simplest answer is probably the best one. If you can explain it with 1 fact, you don't need to explain it with 2. Next, effects that we see, or phenomena, of the same type should have the same cause. If I drop an apple and it falls towards the earth, and I drop a coffee cup and it falls towards the earth, I should suspect that the reason they fall to the earth is from the same cause because the same thing is happening. It's not something special to the apple or the coffee cup. Third, inherent properties that we observe in all cases should apply to those we cannot directly inspect. All bowling balls probably react the same to gravity. We've seen a lot of bowling balls react this way to gravity, so even when we haven't directly inspected, we should assume that it behaves the same way. And finally, we should look at propositions measured and logically deduced as true until phenomena or evidence arises that demonstrate those not true. What that means is, as we make logical deductions or measure something through an experiment, we should take those findings that we've arrived at to be true until something says otherwise, at which case we should reevaluate why those things don't hold. This has turned in modern day to the scientific method, something that you hopefully learned in school a few times. I took this version of 7 steps from the Wake County website of how the scientific method is taught. Scientists are special kind of people, as you can see in this conference, KCD. We're naturally curious and like to ask questions. The very first step of the scientific method is the easiest. You observe the world and nature around you. You might observe things like, for instance, that all objects fall towards the Earth orbits the Earth orbits the sun, and those things should have some sort of cause. Or in the case of this comic, every time this lever is pulled, a lightning bolt zaps the polar. We then have to ask a question. And we try to ask questions that we think we can actually answer. So instead of asking, why does the moon orbit the Earth? We want to ask more specific questions. For instance, objects fall towards the Earth. Do all objects fall towards the Earth at the same rate? Every time I pull this lever, is it the same lightning bolt? Is it the same charge? Does it happen at the same time? These kinds of questions are things we can actually measure. We then turn this question into a testable statement, which has the fancy term hypothesis. It's basically just an if-then statement. Therefore, if we don't see the then, it must not be the if that makes sense. If all objects fall to Earth at the same rate, then 2 different objects dropped from the same height will hit the ground at the same time. This is an example of the hypothesis. And then next, science demands that we do something, poke it with a stick and see what happens. We have to conduct an experiment. In the example I've been alluding to, we could, for instance, go to the top of the North Carolina Science Museum and drop a bowling ball and a brick from the same height and time when they hit the ground. Let's see if those times are the same. After we've done this experiment a few times, we have to go and analyze our results. Here I put down special magical pads that measure the exact time that they hit. I might then conclude that the objects hit at the same time, but I notice that the numbers start to differ in the 3rd digit past the decimal. So they're the same, not exactly the same, at least as well as I can measure. Finally, we can draw conclusions from this data, such as, well, they both fell from rest and fell the same distance, hitting at the same time, suggesting they accelerated at the same rate. Since I picked these objects kind of arbitrarily, this should work for any object on Earth. We then need to share our results. We might post them on the museum website for everyone to see. This can let other people postulate what might have happened from that data, and also perform the test themselves and see if they get the same or different result. So this is an idealized version of the scientific method, and you probably at some point in school used it to perform an experiment of your own. In reality, doing the scientific method is a lot of work. And in fact, it's so much work that you can't get one grad student to do all of those steps all of the time. Our questions become more complicated as our understanding of the world becomes more full, and our questions become much more nuanced and more difficult to determine. So at least in physics, but in most modern sciences, we sort of divide labor amongst three different categories. First are the theorists, which I'm a member of, and therefore it's probably the best in my opinion. And these people use mathematical models and known results to make predictions that are allowed by that set of models and results. We're the ones who help pose questions on a hypothesis that can be answered. And we also sometimes help make sense of data that's measured and offer explanations for why that data turned out the way that it did. We're the ones who do maths on blackboard and paper instead of going out and doing the experiments. That's handled by the experimentalists who work really, really, really hard to measure things that are very difficult to measure. They're in charge of designing and conducting this experiment, which can take years and collaborations that are immense. Some of my colleagues in the experimental part of the nuclear physics department spend years building just one part of a device that has multiple parts and takes a few years to actually run. They are experts at finding ways to isolate the if-then thing we're trying to measure in the hypothesis, and they produce data, and very importantly, they quantify how accurate that data is. In my metaphor or analogy from earlier, they, for instance, would volunteer that their device can only measure to 3 digits past the decimal in time, and so their result can only be trusted up to that level of accuracy. And newly, there's this third category, which is sort of quasi-theorists and experimentalists, computationalists. They perform simulations when direct experiments are not possible. So for instance, we can't toss matter into a black hole. We don't know how to get there. However, we can see what would happen in a mathematical model by using a computer to solve what would happen. They can also help theorists solve problems and equations which cannot be solved on paper by hand. Some of these equations are really, really, really hard to solve, but a computer can grind away at them for a very long time. These three things then work in tandem. And so the scientific process lets us decide how we know what we know. By A, knowing that our mathematical description of phenomena forms a theory. Theories are a collection of evidence and facts and should accurately describe our observations and also make predictions about things we haven't yet observed. The theory of gravity, for instance, makes predictions about what will happen due to gravity on some object, even if we haven't seen it before. Predictions from theories are then tested by experimentalists in the next step and provide evidence that the theory is the correct description by hopefully confirming those predictions. Then we, the community of scientists, reach conclusions together by consensus by sorting through these volumes of evidence. When a paper is published, other scientists might pose alternative explanations or point out things that they think might not have been accounted for, or pose questions that the original experimenter might not have thought of. So slowly over time, we debate back and forth, but then eventually all agree on a consensus as those questions are answered. Then, as Newton described, we use our best available theory until an experiment offers evidence that the theory is incorrect, or worse, that it lacks predictive power. This, I will point out, does not mean that the theory is wrong. It doesn't mean that it can't do anything. It just usually means that it's incomplete. It's missing some bit of knowledge and can't predict some things. When new theories are proposed, we want them to be just as good as the old theory and better. When your iPhone upgrades from 10 to 11, you don't want it to suddenly lose the ability to make phone calls. You expect it to do everything the old version could do and some new stuff. As one of my personal heroes, Richard Feynman, says, theories can never be proven correct, only temporarily not yet wrong. This process is how we determine what we should gain confidence in. So let's shift gears a little bit and start talking about general relativity. Newton, in addition to inventing the scientific method and as a side product calculus, when he was 19, gave us the first subfield of physics, classical mechanics, which is the study of moving bodies. He said a lot of things, but I'm going to give just 3 of them that are important for this talk. First, he suggested that objects have this property that he called inertia. And that's just a fancy way of saying that objects at rest tend to stay at rest instead of spontaneously moving. And objects that are moving tend to stay moving, they don't just randomly stop. He then goes, if you want to switch between at rest and moving, or vice versa, the thing that changes that state is called a force. It accelerates you, changing your velocity, perhaps bringing you to rest or speeding you up. And what Newton was trying to do was describe the motion of celestial bodies. He did this by suggesting the first force, gravity, which is a force between things that have mass. And he gave this very simple equation that says that the force between two massive objects depends only on the mass of the two objects and the distance between them. This solved a lot of problems for the time. This is like the invention of computers and the information age. We're able to suddenly figure out how we should aim things to make projectile motion work. We can aim things like catapults or cannons to hit where we're trying to hit. We can explain how objects gain acceleration or gain velocity in free fall. We can make predictions about the speeds of things and the motion that they'll do. And as Newton wanted, he can predict the movement of planets and how that works. However, there were hints even at the time that something is missing. Famously, Newton was unable to predict this particular precession of Mercury. In this diagram over here, you see that Mercury has this elliptical orbit that slowly changes over time. Newton's theory predicts it should just be one of these gray lines, not all of them, not the one that changes. So this is a hint that although classical mechanics, as Newton posed them, is good for a lot of things, it is still missing something. Then a lot of time passes, and Einstein starts talking about reference frames. Einstein considers an axiom. An axiom is a starting place to make logical deduction, something that you assume to be true from observation. His axiom was that the principles of physics are the same in any inertial reference frame, which doesn't enlighten you at all. An inertial reference frame you can think of as a movie frame. If you take out a camera, you get a frame of stuff you can see. And we do physics on the motion of bodies in that frame. An inertial reference frame is one that is not accelerated. It is either a stationary camera or a camera hooked up to a crane that moves at a constant velocity. This axiom says I should be able to do physics as long as I'm not accelerating my reference frame. Whether the camera is moving or not, physics should work the same way. Let's see a consequence of this. We're imagining that this man named Joey is riding the Newton Express. Joey is riding on an empty train car and he's kind of bored. So he apparently brought a cricket bat. And he's going to pass the time by throwing a ball from one end to the other. And decides, let me calculate how fast that ball moves from one end to the other. How good's my cricket skills? He learned in his physics class from Newton that the velocity or speed of an object is how far it travels divided by how long it took to travel that far. This is why we measure like the speed of a car in miles per hour. It's how long it takes to go a mile in and out. That's not exactly right, but yeah, you get the point. He then measures that his train is 15 meters long, and he uses a stopwatch to time that it takes 3 seconds to go from one end to the other. He divides 15 by 3 and says the ball, therefore, must be moving 5 meters per second. His camera, his reference frame, is in the train with him. And so he goes, this seems fine. Let's consider this same instance of the Newton Express, but from someone else's perspective. Lana, whose camera, or frame of reference, is not on the train, but on the platform as the train goes by. Lana also knows how to calculate speed from physics, and so she's going to take measurements herself. She, with a stopwatch, also concludes that the ball takes 3 seconds to go from one side of the car to the other. But importantly, she sees the ball move further than 15 meters because the train itself is moving. Once the ball is launched, the target, the other wall, moves away from it. And so it not only goes the 15 meters of the car itself, but the 10 meters that the wall moved as the train was moving. She therefore concludes that the ball was moving not at 5 meters per second, but faster, at about 8.3. Well, who's right? Einstein says the laws of physics should work the same in both reference frames as long as they're inertial, which they were. So who's right? Well, both of them are. What happens is we need to recognize that the distance the ball travels is relative to the reference frame there. Joey measured the distance relative to his reference frame on the train and got 15, while Lana, her reference frame was off the train and she saw a larger distance. However, what makes this work is were they to talk later, they could convert their footage from one frame to another. And they would agree then on exactly how fast the ball was moving in one reference frame or the other. So the laws of physics do in fact work the same. We just have to know what we're talking about in terms of the reference frame. Cool. So Einstein says, that's fine, but I have a second axiom. Around the turn of the 20th century, we were beginning to do a lot of things with light. And in particular, we're finding that light has some peculiar properties. Einstein sums this up with this axiom, that the speed of light, in vacuum, mumble, mumble, fine print, is the same in all frames of reference. All observers should measure the same speed of light. Okay, so let's board the relativity express and repeat the experiment from before. But instead of throwing a ball, Joey's going to turn on a flashlight and, ever ambitious, measure how long it takes the beam of light to go from the flashlight to the edge of the car. Lana is still on the platform and is going to measure the speed of light as well. They're going to use the exact same methods before. They're going to measure the distance it travels and the time it takes to do that. We're going to imagine that they have stopwatches that can do this. Well, as before, they're bound to measure different distances that the light travels. Lana sees the train moving as well as the beam moving, but Joey just sees the light moving. So as before, they're going to arrive at different answers. And we once again ask, who's right, Joey or Lana? Well, both, neither. I don't know how to answer this question. It seems like physics is broken. Einstein just said the speed of light should be the same, but they just calculated different speeds of light. This implies something very weird, which is that not just the distance, but also the time that we measure is relative to the frame of reference. And Einstein publishes his findings here as the theory of special relativity. This has weird consequences. Special relativity describes the motion of things moving at or near the speed of light. And it necessitates that we stop considering space, distances, and time as being two separate objects. Instead, it demands a weird thing called spacetime, which incorporates both things as one object, dimension, thing to be measured. Therefore, when two observers in different reference frames measure timings or distances, just as with Joey and Lana, they're going to disagree. However, were they to measure that distance between the events in space-time, they should agree. This means weird stuff. In particular, it implies that time is a spatial dimension. We get around this by converting its units by multiplying it by the speed of light, c. So ct has units of meters, and it's sort of like time distance in space-time. This means that the clock on a moving thing that goes closer to the speed of light literally ticks slower than a clock not moving at the speed of light. In the case of Joey and Lana, the only way to reconcile their different measurements of the speed of light is if Joey's stopwatch ticks slower than Lana's. This sounds like something crazy in mathematical science fiction, but it's real. We can test this and have by taking subatomic particles called muons, which are essentially fat electrons. They normally decay in microseconds, a few seconds. But if we speed them up to the speed of light, suddenly they live much longer without decaying. Their internal clock literally ticks slower compared to us on the outside. There are also some other weird things, like objects observed by someone on the platform that's moving near the speed of light appear to shrink in the direction they're moving. And also, this implies that it's impossible to say for certain whether an event happened before another using just time alone. Using our train analogy, if Joey is riding on a train and two lightning strikes appear to strike the ends of the train at the same time, as measured by Lana, Joey will see something different. He's moving towards the front of the train and away from the back. The light from the lightning bolt at the front literally reaches him earlier than the one from the back, which has further to go. Later, when they talk about these lightning strikes, Lana will say they hit at the same time, while Joey will say the one at the front hit first. Again, they can't agree unless they talk about things in space-time, at which case they suddenly agree. One of the last predictions of special relativity is that energy and mass are secretly the same stuff. And that's all I really need to say about that for the moment. So what does this have to do with general relativity? Well, The special in special relativity doesn't mean that it's like fancy and preferred. It means it only applies if the reference frames are inertial, not accelerating. So Einstein then considers another thought experiment. He goes, what if I lock someone in an elevator with a ball? If that elevator is on Earth and they drop the ball, they'll find that it falls towards the ground with an acceleration that they always see on Earth, which we call little g, about 9.8 meters per second. But what if instead of parking the elevator on Earth, I have a Willy Wonka elevator that can travel anywhere, including through space? If that elevator is moving upwards at an acceleration of g, and I drop the ball, from the perspective of the ball, the bottom of the elevator accelerates towards it with the acceleration g. So then Einstein asks, if you're in an elevator with a ball when you drop it, can you be sure that you're on Earth? Or could you actually be on this rocket that is accelerating upwards at the same acceleration as we find objects fall on Earth? And he concludes that you can't. You can never be sure. There is no difference in what you could measure physics-wise between these two cases. This means that the gravitational force between two objects that causes them to move towards each other is indistinguishable from just having your camera accelerate. This is kind of weird, and Einstein uses something weirder, some work by Bernard Riemann, who did non-Euclidean geometries, so geometries that are not flat, to make this theory possible. In 1915, he publishes the general theory of relativity, which includes accelerating reference frames. And this explains gravity as a consequence of the geometry of spacetime itself. That is a sentence. So let's try and figure out what he means by this. Let's consider two planes that start flying north along parallel routes. We have two planes, and you can see that they're both on course to follow one of these lines up towards the North Pole. Parallel lines, I'll remind you from geometry, are lines which never intersect. They're supposed to be the same distance apart at all times. Well, as they fly up, the pilots start to notice that they're moving closer together, even though they're both going north and were going parallel earlier. In fact, they'll intersect, meeting at the North Pole, something parallel routes are never supposed to do. How is this possible? Well, they realize that although it looks like the surface of the Earth is flat when you're on it, the globe is in fact curved. From their perspective of a flat Earth, it looks like they have a force pushing them together. And this, Einstein says, is what gravity actually is. We are moving through a geometry that to us appears to be three-dimensional Euclidean geometry, but is in fact something weird and curved. And the motion of bodies towards each other is not a force between them. They're just moving on straight lines in this weird curved space. General relativity is an extension of Newton's explanation of gravity. It reduces to Newton's solutions when we're talking about local things, but on the scale of the universe, space-time does some weird things. General relativity makes a lot of predictions, but the two that are most relevant for our discussion on black holes are that A, time moves slower towards more massive objects, meaning a clock on Earth will tick slower than a clock in orbit around Earth. This is in fact so precise that this is how GPS systems work. Satellites at different positions and the clock in your GPS unit share what they think is their local time and calculate the distance between them by how much their time differs, by deducing the height they must be from Earth. Additionally, since space-time is curved, this means that massless things can move in a curve just like massive things do. One example of this is gravitational lensing, the act that light, which we think should move in a straight line, can actually bend around massive objects. Here, there's a very, very dense object, very dense object, and this ring around it is actually the light from a galaxy behind this object. As light traveling nearby comes towards it, it's so massive and dense that space-time is curved around it, and the light bends outward and then back in just like a lens. This technique is so well understood that astronomers and cosmologists actually use it to deduce things about the galaxies that we can't see but that are luminous. General relativity is summed up in Einstein's equations, which are our first step towards understanding Penrose's Nobel Prize. I promise this is the only equation that I'll actually talk about. This equation, which is the triumph of general relativity, is called the Einstein field equation. It has 3 parts plus some constants. The thing in the purple box here is called the stress energy tensor, T mu nu. It has a complex structure. It's not just a number, but don't worry about what it is. What it does is describe how matter and energy are distributed in space-time. This thing on the left in green, G mu nu, is called the Einstein tensor, and it describes how space-time is curved. It describes the geometry. So for our pilot example, if they solved this, they would find that it's on a curved geometry. This thing in orange is the metric tensor, little g mu nu, times this thing called lambda, which is a cosmological constant. This sort of accounts for the fact that we think the universe is expanding, and that will affect our answers. Einstein regretted putting this term in, but we now know that it's probably a pretty good idea. One solves Einstein's equations by specifying the purple box, T mu nu. They go, I'm going to put matter in a configuration, and then ask what G mu nu corresponds to that layout, which tells us how space-time should curve. This is summed up elegantly by John Wheeler, a physicist who should have won a Nobel Prize but never did, that matter tells space-time how to curve, and space-time then tells matter how to move. I want to point out that this equation looks very, very simple, but is in fact very, very complicated. In fact, it's so complicated that Einstein himself was only able to find trivial solutions, meaning he recovered Newton's laws by pretending space was flat and doing approximate things. So he did mathematical tricks. About a month after he published, Carl Schwarzschild, this man here, published the first exact solution to Einstein's equations. He considered an arrangement of matter that's just a sphere and said, this looks kind of like our star from the beginning. It's a sphere of matter which is not rotating, isn't doing anything weird like pulsating, it doesn't have any electric charge. It's just matter in a sphere. And then he solved it and found G mu nu. But the solution he had found has some oddities. Unfortunately, Schwarzschild himself passed away not long after this, and so was unable to see the fruit of his work. Schwarzschild's solution has 2 issues at different distances from the center of the star, which we call radii. The first one happens at the very center. So at the very center of the sphere of matter, there's something where the curvature of space-time seems to become infinite. This is called a singularity in mathematics and is a problem, usually. To understand why this is true, I want you to consider this very simple equation, f of x equals 1 over x. What you do is pick a value of x, plug it into the right-hand side, and then you get a number. So we can look at what happens as x becomes small. F of 10 yields the fraction 1 over 10. Neat. F of 5 yields 1 over 5. Okay, that's a bigger fraction. F of 2 yields 1/2. Cool. F of 1 yields 1. And around now you're asking me what's the point of this exercise. I then remind you that there are numbers smaller than 1. For instance, what's f of 1/2? Well, that's 1 over 1/2, which is 2. The number got bigger. F of 1 over 10 is 10. Well, then what's f of 0? Hopefully you learned in school that 1 over 0 is not defined. We don't know how to answer that question. However, I do notice that as I plug in smaller and smaller numbers, the value of f of x gets bigger and bigger. So f of 0 should be the biggest number. This is not a real thing because infinity is not a number. But we note that as you get closer to the center, the function grows towards infinity. And in physics, we say that this function blows up. This implies that something went wrong. Reality doesn't have singularities. We don't walk around and at the center of massive objects see a spike in things, anything. This is usually thought to be a problem either in the way the equation is solved, that the theory is incomplete, or is an artifact of something we impose to try and solve the equation. The second oddity in Schwarzschild solution is that at a special radius, which we call the Schwarzschild radius, an event horizon emerges. As we mentioned at the beginning of the talk, the event horizon is the thing that makes the black hole so deadly and awesome. It is this part where, if you pass it, space-time is so curved towards infinity that there's literally no path you can take, no line you can follow that leads out. All lines instead spiral in towards the center. This means if matter, say from our collapsing star at the beginning, gets within the Schwarzschild radius, it's going to collapse without end to infinite curvature, and nothing from there can ever escape again. We now know this to be a black hole, and Schwarzschild solution predicts it right away. However, physicists at the time do not like this. We don't like singularities. They're usually a sign that the theory is incomplete, or we assume something that's not true. For instance, Schwarzschild assumes that his matter is arranged in a perfect sphere. Well, maybe that just doesn't happen in nature, and by demanding that, we have made a thing that nature never will, and that's why we get this strange solution. Physicists often joke that they make assumptions to simplify problems that are far from reality. So a joke is to describe the motion of a cow, let's assume it's a spherical cow of uniform density. This is obviously not like the motion of a real cow, which has mass distributed in places and has limbs and is not a sphere. It's very unsymmetric, very hard to solve. The argument essentially goes, we get these weird things because you've imposed this symmetry, not because they're actually real. Well, physicists continue to solve Einstein's equations, and they keep finding things that exhibit black hole behavior. They keep finding singularities and event horizons. They do this for matter that is spherically symmetric, but that rotates. They do it for charged matter. They do it for things that are not quite spherically symmetric. And they still find instances of black holes. In 1931, a physicist named Chandrasekhar proves that compact objects that are heavy enough will always collapse gravitationally, which is what happened with our star at the beginning. It was too heavy, and so gravity just kept pulling and pulling and pulling on it until it reduced down to a point. His suggestion then was they therefore must become black holes. What else could they be? Well, physicists are skeptical people by nature. We really want to make sure that the answer we're using is the right one. General relativity continues to get more ribbons on it. We continue to find more predictions of it which are true, but black holes can only be calculated by hand in specific cases. And astronomers don't really know how to look for something which emits no light at all until the 1960s. Roger Penrose, together with Stephen Hawking, published a theorem in the 1960s. Penrose started his career as a mathematician working in geometry, and he is famous outside of physics for making a bunch of geometric conclusions. He makes objects, for instance, that look like they should be impossible. Penrose proved with this theorem, a diagram from his original paper of a black hole, to the right here, by the way, looks awesome, are not a byproduct of the symmetries we've imposed, or a problem with the way we're solving the equations. In fact, this theorem shows that as long as certain conditions are met, and they're very, very easy conditions to meet, there in fact must be a singularity inside of a black hole. General relativity demands that. It is something the theory predicts, not something that we're doing wrong. This is essentially the mathematical proof that this is a consequence of general relativity. And therefore, if general relativity is correct, which we keep finding reasons to think that it is, singularities, and therefore the crazy behavior of black holes, must also be correct. For this contribution, which brings black holes out of something that we're afraid to talk about and feel like we have to defend, turns it into something that is scientific fact, something we expect to find one day. And in fact, something that people, even outside of the field of general relativity, believe to be true and that we will one day detect. And for this achievement, he was awarded half of the 2020 Nobel Prize in Physics. We're now going to shift to the efforts I just mentioned. Let's try to see a black hole and what that entails. And astronomers are now asking, but really, how do we see the dark? We don't know what to look for. They begin to try and find evidence of black holes. They say, well, since light cannot escape the event horizon, maybe we should just try to find evidence that something is there, even if we can't see it. the tactic goes, let's look for things that look like they're orbiting a star. So we'll see a star orbiting something, but if we can't find anything there, maybe that's because it's a black hole. I summarize this as, we shall know it exists because it leaves footprints behind it. Something must have left. In this image to the right, this black hole pictured at the center has stars which orbit it. However, an astronomer, being able to see the stars, but not see the black hole, but might conclude that there must be a massive object there. A black hole might be a good candidate. Meanwhile, theorists are still doing general relativity on paper, and more computationally. And they begin asking more questions about black holes now that they're confident that they're real. They, for instance, ask, can black holes accrete or eat matter from the nearby star? We see black holes as having this accretion disk around them full of matter that heats up. Is it possible for them to add to that matter in their mass by consuming a star? Further, what if two black holes are near each other? Do they orbit each other like stars do? I mean, they're masses. Why can't they do that? In fact, maybe black holes can collide, merge together to form bigger black holes. Back to astronomy for a second. Since the 1920s, astronomers have been detecting objects which emit radio waves in a directional fashion like a beam in large amounts. They called these objects quasars, and essentially was a way of going, quasars do this thing. And someone asked, what are quasars? And they go, they're the things that emit radio waves. We don't know what they are. Well, theorists who have been working on similar problems suddenly go, hey, I can explain a quasar. Perhaps it's a really, really, really massive black hole, pictured here by an artist to the right. As matter gets caught in the black hole and spirals towards the event horizon, never actually reaching it, it forms a thing called the accretion disk. That matter can get really, really compressed, sort of like our star at the beginning. And in fact, it can get so hot and compressed that it starts emitting radiation, not just light, but other things like radio waves. They then calculate, well, to do this, you would need a very, very massive black hole. As per our story at the beginning of a single star collapsing into a black hole, that black hole should weigh less than or about the same as the star that collapsed. Those are called stellar mass black holes. They weigh the mass of suns. Quasars, on the other hand, in order to do this behavior with a black hole, requires them to be supermassive. They have to have hundreds of thousands or millions of suns mass. We don't really know how that could form. Maybe they do, in fact, collide and make larger black holes, but we don't know that yet. Until now, black holes are thought to have those stars. And so we have to start debating, can you make supermassive black holes? General relativity allows them, but that's a whole different story than actually forming them. And we don't know how you would do that. Black holes tend to be rare. How can enough of them combine to be supermassive, for instance? Back to astronomy for a second. In the 1930s, we invented radio astronomy, telescopes which can detect radiation in the radio frequencies. Carl Yansky, who is essentially the father of radio astronomy, notices that towards the center of our galaxy, in the direction of the constellation Sagittarius, there is an immensely bright object in the radio frequencies. Since it's in Sagittarius, he calls this object Sagittarius A. And you can kind of see here on this image, this is a false color map of radio waves. He sees this incredibly bright thing, much brighter than everything else around. Further measurements in the 1980s showed that Sagittarius A was actually several objects. It turns out that it's hard to look at the center of the galaxy. And the reason is there's stuff in the way. There's what we call dust, tiny particulates of things, which absorb light at the radiations we're interested in and basically make all of our images fuzzy. Excuse me. It's like there's fog between us and the center of the galaxy. With radio telescopes increasing, however, we got a little bit better resolution and decided that the thing that's actually brightest is an object we call Sagittarius A star. We begin to suspect that this too must be a supermassive black hole, since it can be explained similar to a quasar. And so suddenly experimentalists make efforts to try and determine properties of Sagittarius A star. We're going to try, for instance, to measure its mass, see if it would be a supermassive black hole. To do this, a team led by Reinhard Genzel began to try and measure the mass of Sagittarius A by looking at a star orbiting it. His team measured the orbits of a star that they called S2 over 10 years. We are now at this point very good at understanding the orbiting of planetary bodies, both with Newton and general relativity. The way this works is they measure the star over a long period of time. They measure its speed as it moves along its path, and they measure, for instance, at which point it turns around, seeming to head away from the thing it's orbiting. We understand that this speed and this distance relate to the mass of the star orbiting it and the thing that it's orbiting. We then use this, our knowledge of S2 and its orbits, to deduce the mass of the thing that it's orbiting, Sagittarius A star. They conclude from this measurement that Sagittarius A star has a mass of about 4 billion of our suns. 4 billion solar masses is immense, and literally cannot be explained by anything else other than a supermassive black hole at this time. We don't know anything else that could possibly be that massive and emit radiation like this. Another team later, led by Andrea Ghez, used this telescope to my right, the Keck telescope, to measure the same transits of multiple stars orbiting Sagittarius A star. Keck used a bunch of advanced techniques to get sharper images. They're able to figure out ways to get around the fact that there's dust toward the center of the universe. They then do what Genzel's team did with multiple stars, basically getting better and better data. And they agree. They give more decimal points on that measurement, but agree it's about 4 billion solar masses. Genzel's team goes back and does something similar using the orbits of other stars. And together, they provide the strongest evidence that this object, Sagittarius A star, must be a supermassive black hole, something that theory allows, but we don't know how it can be made. And they lie at the center of our own galaxy. Everything in our galaxy is a spiral orbit around this giant, giant, giant black hole. In 2019, we finally caught the glimpse of an actual black hole, a supermassive one, in fact. This image to the right, which you might have seen news about last year, is a composite image that pictures a black hole. This is false color around the edge of the accretion disk and light that's bent by the gravity in radio waves. And we can see the black center where the event horizon swallows all of the light. Further, we finally fill in the missing link about how we get from black holes that weigh a few suns to black holes that weigh many, 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 many thousands of suns. In 2015, the instruments LIGO and Virgo measured the gravitational waves, another feature of general relativity, emitted by two black holes merging together. We were able to deduce the mass of the black holes based on the gravitational waves. And these are what are called intermediary sized black holes. They weigh about 50 or 60 solar masses. And this is the first evidence that we've seen that black holes that are stellar mass can combine together to make heavier and heavier black holes. We are finally able to imagine a way in which a single black hole, the size of the sun, can become the supermassive one weighing 4 billion suns at the center of our galaxy. For these painstaking measurements over many, many years, which astronomers do with too little credit, it's a very, very hard job. These two, Genzel and Ghez, were awarded the other half of the 2020 Nobel Prize for demonstrating that the object in the center of our galaxy is a supermassive black hole, further providing yet another award on general relativity and showing that black holes come in all kinds of shapes and sizes. Really, the shape's the same. It's the size thing that differs. So I asked at the beginning, how do we know what we know? How do we know that these crazy black hole things do in fact exist? Let's recap all of the things that we have that convince us. First, Einstein develops the general relativity using the scientific method. It gains evidence that its predictions are accurate. Over time, we gain knowledge based on general relativity, we make predictions, and we test them. General relativity does everything Newton's mechanics does and more. Next, GR has solutions which predict the properties that we see of black holes. Well, if GR is as correct as we think it is, that means black holes have a pretty good shot of existing. Further, Roger Penrose shows that black holes are a prediction of general relativity, not something we're doing that somehow dilutes the real answer. This basically convinces theorists that black holes are a thing we should look for. We begin with astronomy to see indirect evidence of black holes and start postulating new types of black hole behavior, including supermassive ones. Ginzel and Guess, through painstaking measurements, actually show that there's an object at the center of our own galaxy, which is a supermassive black hole, something 100 years ago was thought ludicrous at the stellar size. We then began to detect intermediate black holes in our merger, explaining the missing connection between how we get from small black holes to big black holes. And along the way, we even managed to photograph a black hole, putting our final nail in the coffin that these things are not science fiction, but science fact. And for all of these incredible contributions, we award some Nobel Prizes this year. So I want to thank the North Carolina Museum of Natural Sciences for having me. And again, I want to thank you for dropping by to learn about physics instead of doing something else. And Chris is going to take your questions, and hopefully I'll be able to answer any lingering questions that you have. Chris?
Everybody, let's give Sam a big round of applause. Drop little clapping hand emojis into the chat box for Sam.
Do it for myself.
Yeah. Fantastic presentation.
Thank you.
I mean, and you did it in under time too, from before Newton all the way through to today.
Yeah, 200 years, it just flies by.
Well, so I see there's questions coming in through the chat, and folks, go ahead, drop your thoughts, questions in there. The ones that are there, I'll be posing in just a second. But I think the next question, and you did such a thorough job, is, okay, well, what don't we know about black holes now then? And general relativity, how it applies to that. Have we figured it out?
No. So one of the biggest remaining questions about black holes, so I kind of snuck it in when I mentioned that nothing can get outside the event horizon, even information. Well, this is a problem. Other fields of physics think that certain things should be preserved. There are certain numbers which, if we counted up everything, we should get the same number. But if it falls into a black hole, we have no way of accounting for that. This seems to disagree with what other fields of physics should do. Stephen Hawking has proposed some things about how black holes can disintegrate and we could retrieve the information, but this is still a very active area of research. And as has mentioned in all science fiction, we have no idea what happens beyond the event horizon. We don't know what space-time really looks like there. We've never been able to see what is called a naked singularity, which is what someone falling into the black hole would observe. And so we know a lot about what happens as you approach the event horizon, but we don't really know what would happen as you cross it. For instance, we think that your version of time should stop before you ever reach the event horizon. You just freeze. Time starts to mean different things. So there are a lot of open questions. There are more complex black holes than I've described, but these are a little bit beyond me in terms of what the active research is doing in those fields.
Okay, wow. So they just get weirder and weirder and more difficult to understand.
Problems tend to get more fascinating and harder at the same rate.
All right, let's see. One of the first questions that came up in the chat early on in the talk was when you first mentioned Sagittarius A. Is Sagittarius A the same black hole in Cygnus?
Yeah, so now I show my ignorance about astronomy. So Sagittarius A star is on the border of Sagittarius and another constellation, which I can't remember the constellation, but I do think Cygnus is in it. So probably it's like kind of between the two, and we now know exactly where it is. It's not even in Sagittarius. It's just how we marked the direction originally.
Ah, okay. Okay. So if somebody wanted to look up at the night sky and think that they were looking at a black hole.
We also think that there's smaller black holes orbiting Sagittarius A star, so he could be referencing could be referencing one of those.
Oh, okay. Well, okay. Well, so if I go out and I look up at the night sky, what are the chances that I'm seeing a black hole in my field of view?
Well, seeing and detecting are two different things. So
true, right.
It's not emitting a lot of light that we can see. That dust really scatters a lot of the visible light. There's a bunch of stuff in between us. And so Sagittarius A star, when I say it's very, very bright, it's very, very bright in a specific frequency range of light. And that range is radio, which is something we can't see. So this is not something you would see with like a visual telescope that uses lenses. This is something you see with an array of satellite telescopes that together measure the radio waves emitted. But given in any direction that you look, there's probably a black hole along that line of sight somewhere, but not something you'll be able to see with your naked eye or even a very good optical telescope.
All right. Excellent, excellent. Okay, Emma says, I still don't quite understand how black holes interact with objects around them. So they don't suck things in?
Yeah, so black holes are often depicted as these vacuum cleaners, which just pull from further and further away.
Mm-hmm.
They behave more like other objects, like stars. They have gravity, but if you get far enough away from them, they just look like massive objects. So they don't pull any more than a star their size would, or their mass would. What makes them different is as you get closer, instead of space-time being kind of gently curved around them, it gets contorted and twisted. And so light does weird things near them. The paths you can follow, the like available routes you can possibly take, all spiral towards the black hole. And so they're not vacuum cleaners. They're literally a thing with a fence that says do not cross or no one will ever see or hear from you again, which makes them, in my opinion, kind of cool. If that answers your question.
I think so. And it leads to another one that Emma wrote a little bit earlier. Is there any reason to be concerned about the mega super black hole?
Nah. So you made the joke at the beginning that maybe there's some black holes near me, and I went, oh God, I hope not. So supermassive black holes are a problem when you get near them. For one, they emit radiation that's bad for you. Second, as you get closer and closer, the gravitational shear becomes stronger. And what that means is, normally we think of gravity as being gentle. So the Earth pulls on my head and my feet at about the same rate because the gravity is weak enough, the difference is very, very tiny. However, supermassive black holes, that distance over which gravity changes becomes shorter. And so if you get towards or too close to a supermassive black hole, your feet can fall towards it faster than your head. And you get stretched out in this process we call spaghettification, which is not a word I made up, but a real term that we use. So as long as you don't get too close to a black hole, you're okay. The fact that there's one at the center of our galaxy is just fine. In fact, there's one at the center of most galaxies that are spiral shaped.
All right, excellent stuff. Let's see, what else have we got here? Well, my chat moderator has a question. Does the recent loss of the radio telescope in Chile, is that right?
Arecibo.
Yeah. Arecibo, yeah. Does that hurt the field of astrophysics?
Oh yeah, I mourn for it like a person. Arecibo is a fantastic telescope. And for those of you who don't know, it's a giant concrete dish, and it's a radio telescope that uses this dish to focus radio waves. And it's supported by these massive cables. One of the cables, or rather the tower, collapsed and it broke in on itself, cracking the dish. And so the instrument can't be repaired. It's gone. And a lot of people were using that. So yes, it impacts all of us negatively when we're all very sad for it. There are always plans to build newer and bigger telescopes though, and I'm sure that we'll get something else eventually, but I'm sure astronomers are much more upset because now they have to fight for time over fewer telescopes. And so we're just getting less data, which is always bad.
Yeah, I saw that news and it was very sad. Mm-hmm. Even just to see like pictures of Arecibo are just so magnificent. Yeah, just a telescope that size in the Chilean countryside. Amazing.
It's not often we build these giant things and they break like this. We're used to it with things we send into space, but this is the first time I remember of a telescope on Earth or a massive science instrument just breaking. It was unexpected, to say the least.
Yeah. So let's see. Lex wants to know. Lex writes, sometime last year, they used telescopes from all over Earth to take a picture of a black hole. You showed us that image in your slideshow. How did they manage that?
A lot of work. So that image is not as simple as taking a picture of the camera. It's a composite image. So they essentially took a lot of pictures from a lot of different angles and a lot of different wavelengths, and then figured out how to stitch them together to produce the image that we saw. That image required more processing than the data took. That achievement in that paper is actually about how they figured out how to take all of this data and link it together in the correct way. It took an enormous amount of data and an enormous amount of work. And it's one of these things where the only way to image this is to do all of this information more than one camera can provide. So I can't speak to the exact technical details, but it was an impressive thing that required, as mentioned, all sorts of telescopes from all over the Earth.
Yeah, really, I mean, really impressive feat.
I believe they also published it in the computational science paper version because the computational science was almost as difficult as the physics observation.
So it really wasn't about getting that little image that was the headline, first picture of a black hole. It was about actually figuring out how it all works, how to pull all of the information in together. That's fascinating.
Yeah, this is one of the amazing things experimentalists do, right? Is they figure out how to do what seems to be the impossible. And so one of the things we celebrate is how they managed to do it, not even the fact that they did it and measured something.
All right. Any final thoughts before? Oh, wait, let's see here. It looks like I maybe have one more. Okay, Julie has written, oh yeah, I have to ask you this one. Julie wrote, my son used to have nightmares about getting sucked into a black hole at age 6. How close is the closest black hole to Earth, and how many generations from us should be concerned, if any?
The odds of Earth ever gravitationally interacting with a black hole during the span of humanity are very small. It is hard for things to collide in space, even though galaxies do collide. When they do, it's mostly empty space, hitting empty space. So unless we develop some technology that is very Star Trekian, I don't think any of us will ever get close enough to a black hole in our even generations beyond us. We are safe. It's fun to read novels about getting close to black holes, but that part at least is still science fiction.
That's a good note to leave it. We're going to be all right. And we'll be all right, and we will carry the knowledge of all this incredible science with us forward on into the future.
Hopefully.
Hopefully, very much.
And on the shoulders of giants.
Very much so. Well, Sam, thank you so much for delivering this lecture to us and sharing all of your information and research on one of the universe's most fascinating things.
Yeah, this was a great pleasure. Thank you to everyone who came out, and thank you for the questions. They were great.
Thanks for tuning in, everybody. I'll remind everybody that we do lots of virtual live events right here on the museum's YouTube channel, so you can subscribe to the channel, click the little bell to get notified when we're doing new events. For example, tomorrow night at 7, we'll be talking with the author of Wicked Plants, Amy Stewart. So that conversation ought to be a lot of fun. So join us here again tomorrow night, 7 o'clock, right here at the museum's YouTube channel. And check out naturalsciences.org for more virtual events and more science you can do at home. The museum is open right now as well, so you can learn about how to get your free time ticket in order to come visit us here in downtown Raleigh or in one of our satellite locations at Prairie Ridge or Whiteville, North Carolina. All that information is online. And of course, you can always follow the museum on social media. We're on Facebook, Twitter, and Instagram as @NaturalSciences. Sam, if people wanted to follow your astrophysical work, how could they do that? Is there a way?
Yes, you can follow me at @SamDFlynn on Twitter or SamuelDFlynn.com.
There you have it. Sam, once again, thank you very much. Thanks to the folks with the Department of Physics at NC State for helping put this together and getting the word out about it. And thanks to the museum's digital media team for helping us broadcast this program. That's it, everybody. We'll see you next time. Stay safe. Take care. Good night.